Okay, so let's take a look at the entropy function. The entropy function is a very important function in the field of information theory. This entropy function was put out by the father of information theory, Claude Shannon. This entropy is basically the measure of uncertainty or randomness in a given dataset S. Say a dataset S has some n attributes a1, a2 to n. The entropy of the dataset S would be the amount of the predictability of each attribute in the set. That's basically entropy. Higher the entropy, the more unpredictable your dataset is with their attributes. The lesser the entropy of the dataset, the more predictable are the attributes in the dataset is. This is the formula for calculating entropy, and we will go through this a bit later in this entropy function. So yeah, so let's take a look at the two datasets, S1 and S2. So we have dataset S1 with 4 attributes A, B, C and D. The probabilities of occurrences of A, B, C and D are here. They are all equally likely. Say in the first time it puts out B, next time it puts out A, next time it puts out D, again it puts out B or C. Say we want to find the next value in this dataset that the machine 1 puts out. So let's try to find the number of guesses that we want to do to find the next number that it puts out. First, let's ask whether the next number is either A or B. So if we get a yes, it means it's either A or B. It's not C and D, right? So now we can ask another question: is it A? Now we're sure that it's A or B. Now we need just one more question to be sure whether the next value is going to be A or B. So we can ask whether it's A. If it's yes, then we are sure that it's A. Say we get a no here. We know for sure it's B because it's A, B. That's true, but it's not A, so it has to be B. So what if this goes wrong? It's either C or D. So now we can ask one more question: whether is it C or D? Is it C? If it gives yes, then it has to be C. Otherwise, it has to be D. So the expected number of guesses, or the weighted average of guesses required to correctly guess the next number, is logically the probability of occurrence of the number. Here all probabilities are equally likely, they are all 0.25 times the number of questions required for correctly guessing SI. So what's the number of questions required to answer guess the value of attribute, say B? How many questions did we come through? We came through one question. This was question 1 and this was question 2, right? We came across these two questions, and in this order we could find the value of B correctly, right? Take D. Questions for correctly guessing either of the attributes here, because their probabilities are the same, is 2. They all require 2 questions to be answered correctly. So when we sum all them up, 0.25 times 2 plus all the same thing for all the four numbers, we get 2. So the expected number of guesses required to correctly answer or correctly predict the next value put out to this machine will be 2. So in 2 guesses you can correctly say whether it's going to spit out A or C or D or thing. This expected number of guesses is what is called the entropy of the system. The entropy of this dataset is 2. Take this machine 2, a dataset S2, which has the 4 attributes A, B, C and D, and the probabilities are given here. So if we want to find out the next number, the next attribute put out by this set, let's ask the highest probable question: is it A? If the next number is A, then we have found the next attribute, it's just A. Say it's N. Let's say it's no. So let's look at this is done. So let's look at the next highest probable number. That's 0.25. So we can ask, is it D? So if we get an S, we were sure that it's a D. If it's no, then we're left with these two. So we can ask another question. We can ask whether it's B. If it's yes, it's B. Otherwise, it's C, right? So the expected number of guesses here required to guess the next number correctly would be the probability of the occurring element and the number of questions required for correctly guessing the element correctly. So let's take the example of A. Probability of occurrence of A is 0.5, half the time. How many questions we need to come across to find whether it's A? Just one question, right? If this question was true, then we can just say we have found the next element is A. So we needed only one question to find out whether it was A or not. So that's this 0.5 times 1. Third question. How many questions do we need to come across to find whether the next number is a D or not? So we need two questions to find whether it's a D or not. So that's 0.25 times 2. This is already done. So now we are left with these two, B and C, of equal probability. So we need to ask just one more question to find whether it's B or C. Is it B? If it's a yes, it's a B. If it's a no, it's a C. So we need only 3 questions maximum to find out whether it's a B or C. So this calculation comes up to be 1.75. The expected guesses, as I said here, the expected guesses required to guess the next one is called the entropy of the system. So the entropy of this machine 2 is 1.75. Entropy of this machine 1 was 2. So probability of occurrence of A, and this is the number of questions we needed to come across to guess whether it's A or not, right? So this is 0.5. P was half. It's 2 power minus 1. Log P would be minus 1. Log to the base 2 minus log would be 1. Check out this probability, P of B, 0.125. We needed to come across 3 questions to find out whether it was B or not. So let's do that again. 1 by 8 is 2 to the power minus 3. Log of 2 to the power minus 3 base 2 negative log is 3. That was the number of questions we needed to answer whether it was B or not. So the number of guesses required is the negative logarithm of the probability of the data set. Where did we see this? We saw this here. Probability of occurrence of an ith attribute times the negative logarithm of the ith attribute. The summation of all would give us the entropy of the data set.